Alright, so let's first of all take some questions. There was actually a question that came up in first period that I told him I'd have to ask about, and I got the answer between periods. But one thing, and I know I did not make this distinction, okay? Some people will say that the limit in the case of 2b2 here, the graph goes up infinitely as x approaches infinity. Okay? So some people will say that it has an infinite direction. However, if you checked your answer in the back of the book, it'll say that the limit does not exist. And that's because the limit actually would have to equal a value. Okay? So it's approaching infinity. However, we would not say that it equals infinity because you can't, it's not, infinity isn't a value that you can equal. Alright? So it goes in an infinite direction, but the limit, we would then say, does not actually exist. Okay, so that is a distinction that I know I did not make, so that's something you'd probably want to put in your notes if you haven't, or since we haven't made that distinction yet. Okay, so that occurred here. It also occurred here on 3, the first part. The limit as x approaches negative infinity of 2e to the negative x minus 3. Okay. So you see our answers here. The sketch is over here. This horizontal asymptote would be at y equals negative 6. Okay. We would actually be crossing e to the x typically crosses at 0, 1. So this is going to cross at 0, negative 5 since the whole thing was shifted down 6 spaces. Okay. So. Now, one thing I do want to point out is, as you look at this one where x is approaching infinity, the limit as x approaches infinity of 2e to the negative x minus 3. Now, why does that equal negative 3? Here we kind of have some, we have to look at the negative exponent. And I used an example of, let's let x equal 1,000. And actually we tried punching that into the calculator and it's so small we had an overflow error. So we even did just x equals 100. And we got something like 7.4 times 10 to the negative 44th power. Okay? Which is essentially 0. And that negative in the exponent there means we're dividing by e to whatever power that is. So 2 divided by this huge number is going to approach 0 by itself. And by the way, this is where that limit of a sum theorem we were talking about yesterday can be helpful. You know whatever you get, you're just going to subtract 3 from it, because the limit as x approaches infinity of 3, that's the limit of a constant, is the negative 3. Okay? So you just have to figure out that 2 over e to the x part, and as you look at it, we have that asymptote. It's going to end up looking, the graph of this function down here we have this asymptote at y equals negative 3, and it's going to end up looking like this. Okay? So that's why as we approach negative infinity, notice it's going up infinitely in the infinite direction, so we would say the limit does not exist. As we go to positive infinity to the right, we're approaching that asymptote -3. Charlie?
So like we would need our graphic calculator to be able to see the graph. Like we wouldn't just be able to like do it by looking at the thing.
Well, you actually can just do it. If you think about what the values are going to be, we're dividing 2 by e to some power here, because it's 2e to the -x. So as you think about that, alright, e to the x is going to get huge, so 2 over something huge is going to approach 0. Alright? Now, for our quiz, I am going to let you use your calculators tomorrow, but actually, if you do think about it, and then you guys know this is just a variation of e to the x, which e to the x is one of our parent functions. So it has an asymptote at y equals 0, it goes through the point 0, 1, it looks like that. So if you apply the different transformations here, it's stretched vertically times 2, it's reflected across the y-axis, it's shifted down 3. You can actually sketch it yourself if you know the parent function. Question?
Yes. So if you're going to negative infinity for the first one, if you put a negative number in for x, does that change the exponent to a positive? Is that not?
Yes. Right here?
Yeah.
Yes. Because it's negative, negative, and that's why e is getting so big, and that's why the value of the whole function is getting so large. Okay? Any other questions? The ones up here on number 1 were pretty straightforward. Although we did look at the graph for this one here for E. So it's kind of an interesting one. There were no vertical asymptotes because x squared plus 1 is never going to equal 0 as long as you're using real numbers. Okay. So there were no vertical asymptotes, but there was a horizontal asymptote at 1. So you see, it's kind of like we would have a parabola, but because we divided, it kind of topped it off, and then we just started approaching the asymptote from the bottom on both sides. So kind of an interesting looking graph. Alright, so anything else from homework? Alright, then, what I want to look at today is we're actually, I know it says 14C, we're actually going to be looking at the concepts covered in C, D, and E kind of together. They're so closely related, I think the book kind of takes a little too much of a baby step approach to it. And it'll actually make more sense if we put some of these concepts together and make some observations along the way. Okay, so you'll notice here it says 14C, rates of change. And one of the things to understand about a derivative is it's going to be giving us rates of change. Okay, that's what derivatives are. Now, your book has this investigation, and I actually modified it from what's in the book because I didn't like what they had. I wanted to be a little more specific. So, what we're gonna look at is a rate of change as we have this free falling object. Okay. If you look at the investigation, it says a ball bearing is dropped from the top of a tall building. The distance it's fallen after t seconds is recorded, and the following graph of distance against time is obtained. Alright, so here we have it. The distance it's falling is increasing. Alright, And what this says is after 2 seconds, it's fallen 64 feet. After 4 seconds, it's fallen 256 feet. Okay? And so on. Alright? Now, we've chosen this fixed point F at time 2. We picked M where time was 4. Okay, and I gave you the function here, d of t is 16t squared. Okay, so the distance traveled at time t is going to be 16 times t squared. Alright, now, question before we go any further. Which hurts more, falling from 5 feet or falling from 20 feet?
20 feet.
Okay, why?
Because
Keith done it.
acceleration.
Alright, acceleration. The acceleration of gravity means that if you fall from 20 feet as opposed to 5 feet, what happens when you hit the ground?
You'll hit it harder,
You're hitting it harder because you're traveling
quicker.
faster, yeah. Okay. I actually did fall out of a tree from about 30 or 40 feet up one time.
How are you,
Wow.
like,
I landed flat on my back and I hit a few branches on the way down, so that slowed me down a little.
Oh my god.
wait,
I
why are you,
landed flat on my back on it was the grass clipping pile underneath. So it still hurt, but
wait, why were you 40 feet up in a tree?
because I was climbing a tree, I was
That's
like
cool.
9 years old or something like that. We climbed trees when I was little. We used to like swing trees and
That's-
jump from
that's
one to the
high.
other.
You get, like, I can get like 9 feet maybe, but
Yeah, it's fun, but yeah, you don't want to do that because it does hurt a lot more when you fall from high than if you're falling from 5 feet off the ground. And it all has to do with speed. So here's the thing. Let's say we wanted to calculate how high up could we fall from and still not get hurt. You know, part of that whole calculation would be figuring out what speed we would be hitting the ground at. Okay? Obviously, another part of that would be your weight and all that stuff, because force equals mass times acceleration and all that. So the mass would be involved there too. But what we can do with in this case is we can actually look at an average speed over an interval. Okay? Now, if I'm 64 feet, if I've fallen 64 feet at 2 seconds and 256 feet after 4 seconds, how would I figure out the average speed in that time interval? What about distance?
Over time.
Okay, the distance traveled over the time, right? So how would we figure out the distance traveled?
Between M and F.
Yeah, between M and F.
Speed times time.
distance formula.
Subtract initial from time.
Okay, yeah. We were initially 64 feet down, now we're 256. So if I do 256 minus the 64, I know that I've traveled a total of 192 feet in that 2 second interval. Okay? Now I have to divide that by the amount of time that's elapsed as well, which is how long?
2 seconds.
2 seconds. Because this occurred at 4 seconds and we started at 2 seconds, so 4 minus 2 is 2. So my average speed over the course of that interval is what? 96. And we would be in feet per second. Okay? So on average, in this case the ball bearing is falling at 96 feet per second over that interval. Now, where is it falling the slowest? At the beginning, and it's falling the fastest at the end, alright? But on average, we're going 96 feet per second. Okay? Does everyone understand that so far? Now, the challenge here, okay, the challenge here is, notice this does not tell us the instantaneous speed. In other words, let's say it hit the ground after 4 seconds. How fast was it actually traveling? Would it have been traveling fast enough to put a crack in the concrete? Okay, which actually if you drop it from high enough it would. Yeah, they've done it with skyscrapers. It doesn't have to be like a skyscraper.
Or would it be shot the ground with a BB gun? Would it crack it also?
Not sure, because the BB gun's so light. But I think they've been able to do it with a penny. But
Actually, kill someone with a penny if you drop it from like the Empire State Building or something.
I've heard that.
you might, the wind catches it a lot, so that would be a little bit
Like
different.
technically,
But
like you could.
if you did a ball bearing, you probably could, because a ball bearing would have no wind resistance, so it would just fall. But
You're in the back.
anyways,
The back.
we can't find instantaneous speed, alright? We don't know how fast it was going at the 2-second mark, we don't know how fast it was going at the 4-second mark, alright? But you'll notice we found that speed by connecting 2 points and finding what? What is this that we actually did with those 2 points?
Found the slope.
We found the slope. If you remember back to your pre-algebra or algebra 1 days, slope is a rate of change. Okay? Slope is the rate of change. Alright? So here's what I want you to do. I want you to take a couple minutes and work with somebody here to complete this, alright? What I want to do is I want to actually shrink the interval of time. If I wanted to figure out the exact speed at 2 seconds, I could actually approximate it by moving this point M closer and closer and closer, right? So instead of this long time interval, if I made t equal to 3, then I'm only looking at this time interval. Okay, so there's not as big of a difference. That means my average will be closer to what the speed was at 2, right? Does that make sense? Okay. If I cut it down even shorter, I'll get an even closer average and a closer average until, what if I move this point right on top of it?
It's 64.
Okay. This segment would no longer be connecting, it would just be like this. Okay? That's actually what we're looking for. Okay? We're getting a little bit ahead of ourselves, but that's eventually what we're going to look for. And we're going to do that by getting closer and closer and closer to 2. Alright, so take a couple minutes here. Find d of t. Remember, d of t is 16t squared. Alright, so for each of these values of t, find d of t, and then you'll have a point. And I want you to find the slope from point F, 264, to this point that you just found. Alright? Use your technology to help you out a little bit. That'll make it go a lot faster. Okay? And feel free to work with somebody. If you want to find the points and then your partner can find the slopes as you get the points or whatever.
Yeah. Start at 0.
tape the two and then go up by one like that. And table set.
How do I search for two?
Second. And you should, if we keep going all the way up to 3.5.
Yeah, it's giving the syntax error.
Five, but not six.
Oh no.
You do that.
There's random
Oh, yeah.
Table. Good.
That was dual effort, don't take full test. We played the number 15 team in the nation yesterday, Gibbon, and Louis, you know Rick Pitino?
Yeah.
Louisville's head coach, he was there.
Really?
And so was Bo Ryan, who's Wisconsin's head coach.
Where did you guys play here?
Yeah. Wow. Crazy.
That's
The
cool.
kid that they were watching was amazing.
I think that
He was so
There you go.
in the first half it wasn't horrible, and then the second half it got bad.
What
We
was
fell
that, what
apart.
was the final score?
We lost by like
42,
But
but it's not a
we lost by like 10.
That's not.
I mean, we
Well,
You got 42
their
points.
defense wasn't amazing, but their offense was amazing.
Yeah. That's not terrible.
Yeah.
When I was coaching, there were two times where we lost by 50.
I don't really think
Because
that's.
the other team just.
They could have beat us by
incredible
more
player.
if they had, right, if they had pressed us.
Wait, what's that? Yeah, I mean, they got fancy towards the end.
Yeah, they weren't like gonna run it up.
They were trying to like throw.
Alley-oops to
Alley-oop,
themselves
yeah.
up and back and away.
They could have easily had
100, easily had 100.
if they had just kept.
And you
kept
can,
If
like,
they
grab
tried
it
to
and-
go
Right.
The kid has like 32 points, but he could have had 50.
I was reading about this kid. He's a sophomore in
And they
high
have,
school, and he's
GI
7 foot
inspired hats.
already.
Oh,
We played against the 8th grade, he's 7 foot,
They
and
have
he's
that
pretty
as
good.
an exam,
He can
so-
actually already, he plays
still
like a
solves
guard
equations.
does, and he can actually handle the ball and everything. It's crazy.
I
Yeah.
just forget how to do it. I have to remind myself how to do it before I can get to
Alrighty, let's take a look at these. Okay. What's D of T when T is 3.5?
Yeah.
100, Jay, what was it,
That's right.
196.
196. How about at 3? 2.5?
1.
2.5?
100? Okay. 2.4?
92.16,
2.3?
84.64,
Then start at 2.
2.2?
77.44,
And 2.1?
70.56.
Okay. So then, those were points that are getting closer and closer and closer, giving us a smaller and smaller interval. Okay? So when I'm finding the slope from F to this point, I'm finding the average speed over that interval. Okay? So at 3.5, what was the slope to that point? 88? Okay? How about to 3?
80.
80 to 2.5, 2.4, 70.4, 2.3,
68.8.
2.2, and 2.1. Wait, what?
65.
Oh, 65.5. Okay. Oh, 1.6?
It was 65.
65.6 you said? Okay. Alright, so you'll notice it's getting smaller and smaller and smaller and smaller. The actual result here, the actual speed at time 2, actually ends up being 64 feet per second. Okay? If we kept getting smaller and smaller and smaller, this is approaching 64 feet per second. And you guys will find out later how to actually find that. But we got 64 feet per second. So, let's think about what we're doing with the slope. Okay? The slope, we're taking that point F, right? 264. And we're plugging in different values of t, and obviously then d of t for the y coordinate. And what are we doing as we're doing this? Mathematically, what are we doing here? We're making t get closer and closer and closer to 2. So what are we finding?
A limit.
A limit, okay? We're actually finding the limit as t approaches 2 of the slope. Okay? Now, you guys can see here, there's a problem with that because it can't equal 2. Alright? It can't actually equal 2. Now, if you look at what we did yesterday, though, for the last couple days, with our limits, if I actually plug in what d of t is, d of t is 16t squared, what could I do?
You could use the rules that we have, so the degree is larger on the top. So there's, you're gonna know that it's not gonna have a horizontal asymptote.
It's not going to have a horizontal asymptote, but we're not approaching infinity. So you're right, there is no horizontal asymptote, but we're not approaching infinity here.
Could you see if that's a hole?
We could see if it's a hole. How do we know if it's a hole?
If you factor the top and the two cancel out, you get a t minus 2 on the top.
Okay, good. So let's try that. How does the numerator factor here? Do you see it?
Yeah, you take out a 16.
Take out a 16,
get
and you have t squared
minus
minus 4. What's t squared minus 4?
T yeah.
Yeah, t plus 2 and t minus 2. So that was actually a hole, which if you think about it, it makes sense. We could, if you go to points to the left of f, we could find the slope of those, no matter how close they are. It's just at that exact point, we can't because you're dividing by 0. Alright? So, that cancels out. What's the limit as t approaches 2? Now,
16 times 4.
16 times 4, which is 64. Feet per second. Okay? Now, what we're developing here actually is the definition of derivative. Okay? And this is not exactly it, but this is the concept behind it that I want you guys to see. See derivative as a rate of change, and derivative is the limit as we're finding the rate of change between points that are getting closer and closer and closer together. Okay? We'll see technically how to do that tomorrow. But I want to take the time that we've got left here and kind of just talk about the derivative itself, and kind of tie together some of the things that I hope you picked up on in the observation or in the investigation here. First of all, the basic concept of the derivative is that it's the slope, it's the rate of change at a given point. And to find the rate of change at a given point, we're finding the rate of change of the tangent line at that point. Okay? Remember, a tangent line is a line that intersects a function at only one point. You could think of it as though it just barely touches the function. Or if you had a ruler or something, or you would just lay it on there, and whatever point it hit, that would be the tangent point. Okay? The point of tangency is the technical name for that point. Alright? But here's the thing. If we find the derivative of the function, and then we evaluate it at the point of tangency, we know the slope of the tangent line, which is the rate of change of the function at that point. Okay? Now, it's kind of a question to think about. Why are lines straight and other things curved?
Oh,
you mean in this situation?
if the
Well,
slope
in
changes,
any one.
if the slope changes and begins to curve.
Okay, if the slope changes, it starts to curve. One of the things you learned back in pre-algebra or algebra 1 is that the slope of a line is constant, right? It's not going to change. So that's why lines are straight, because it's going at a constant rate of change. Alright? With this curve here, we have our slope changing at every given point. Okay? Here we're going up. If we looked at our different tangent lines, you know, here it's going up very quickly. But then it starts to slow down. Okay? What's it going to be when we're at our peak? 0. And then it starts getting to the negatives, right? And we'll look more closely at this later, but you can actually follow and look at the signs of your derivatives. I know that all my derivatives are going to be positive because if I draw the tangent lines, they're all going uphill. And then at the max point, it's leveled off, it's 0. And then it starts to have a negative derivative. Okay, the value of the derivative would be negative as I move on from there. Okay? So, a couple other terms that you need to be familiar with. Differentiation is just a big term for finding the derivative of a function. Okay? If something is differentiable, that just means we're able to take the derivative of it. Okay? So those are two terms that seem big, but they're not but they're not super complicated. But those are terms that you need to be familiar with because they come up a lot. Okay? The last thing I want to look at today, and then I'll give you times. I gave you one problem to work on for homework, but some notation. Okay? And then tomorrow we'll actually get into developing the definition of derivative and making some other observations there about it. Okay? Some notation. Alright? Let me do this just so you can bump it up. Okay? If we're writing a derivative, if we're looking at notation here, f apostrophe, if you will, x of x we would read that as f prime of x, or I noticed your books also refers to it as f dash of x. Okay? I think that might be a British thing or something again. But typically you'll hear it read f prime of x. And then we also have this other notation, dy dx. Okay? And that means the derivative of y with respect to x. Okay? Now, you can also have just the derivative with respect to x, and you can use that particularly when you have multiple variables or something like that in there. That's a little more general. This is specifically saying the derivative of y with respect to x. Okay, but both of those describe a derivative, and you should be familiar with both types of notation. Okay, so that's all that we're going to do today. We'll pick up with the definition tomorrow. In the meantime, I gave you problem number 2 on page 353. Let me bring that up here. Using the method in investigation 3, okay? Find the limit there, okay? So, I'll give you guys the last 6 minutes or so to look at that, and then you can be dismissed when the bell goes.